Hello, I'm Jerry Brito and this is my COMP8210 Big Data Technologies Assignment 1. So, for Section A Document Databases Part 1, we created a Python file which is this one tweets underscore play clean.py, which is the Python ingestion that we connected to MongoDB Compass. So we do the setup, we import the files, we read the 10,000 tweets one JSON file, which is the original file that is given in the question. We create helper functions to clean those, and we use a normalizer, and we return all this id string, time zones, raw text, strip text, and all that. And the main function is here. This answers all the part A to D questions. So for the A questions, we read the raw text and clean the pre-clean the wrappers. We connect a MongoDB and create collections as required, and we ingest raw and normalize to stage in each batches. And for the B question, deduplicate, we keep the newest tweet per id underscore string to tweets underscore clean, which is the clean file that we created now. And for the C question users, we split the user profiles, latest per users, to users, which is the collection that we created now. And indexes as required, create underscore index, these created underscore add, hashtags, which is given in the questions for us to create. So when you run this code, you can either run or go to command prompt and Python space whatever the file name, in which our case is tweets underscore clean.py, and click run. This connects to our MongoDB if whatever URI that we given is correct, and this creates all this created collections that you see here. Tweets underscore clean, which is our clean file, tweets underscore raw, which is our raw file, tweets underscore stage, which is our normalized stages, and users, which has the users details. So you can see the difference between the raw file and the clean file here. So here we open up the MongoDB shell, which is where we write our queries. Moving on to part B, emerging hashtags week over week growth. This code here, so what we do here is we find the latest tweet time in the dataset first, created underscore art, and we convert that max date into this format, UTC. We build window boundaries as required of the question. We self-join into tweets underscore clean. We filter out all the noisy tags. We count per hashtags, how many in week 1 and this is week 2. And we sort out by most interesting growth. This variables here, this is changeable. So this is here, this is kept as per the question. So when you run this code onto the MongoDB, not here, MongoDB shell, the top 10 emerging hashtags. So you can see the growth rate reducing from 2.8 to 1.8, 1.0, all that. This is the top 10, these two images of the top 10 emerging hashtags. Second question B, coordinated link burst. What we do is these two are the parameters, look back hours and threshold, the 3 users and the hours. It's over here. For each tweet, look up other tweets to that same domain. And for each window, count the distinct users and keep a small sample of tweets ID, which is required for debugging if you run into any errors. We clean up the output and sort, which returns. So the problem that we had for this question is we can't find any users, which is as given in our question. We have to use more than or equal to 3 users, but we didn't find any records for those. So we use 2 users and 60-second window is the same, and we found this as the output. Moving on to BC, high volume near duplicates per user. So what we create a pipeline for that question, and what this pipeline does is we keep only tweets that have user and non-empty clean underscore text. We convert the created underscore art into UTC day. We lowercase the clean text again, if you didn't before, and we group by user ID day text, which is over here, to count the duplicates. We sort them and show the biggest repeaters first, then by user day. When you run this code onto the MongoDB shell, we get the outputs over here. The problem that we had with this BC is the question required to use more than 5, but since we didn't have any users more than 5, this is a proof that shows that the maximum users who did near duplicate daily is 3, input as 3, and we found this. Part C, advanced integrity and coordination detection, which is sock puppet signals intersection based. We first create a helper index. By creating these indexes, we can run the query faster. Otherwise, before that, it just kept on running and running and running without any outputs. So we add a unique compound index, and we use extra indexes for fast lookups. Same thing. And here is the sock puppet detection by shared location. The logic that is used for this function is for each day location, we take all the users, we compare all users pairs, we count how many hashtags they both use, and keep the pairs with greater than or equal to minimum support. And here is sock puppet detection by shared URL domain. So similar to the above, the same thing. Instead of using the location, we use the domain. There's not much of a difference, just that. This one, pair of users sharing locations over here, and pair of users. This is just a part of it. It returned more than that. I just took a little bit as a sample, for example. Cross account promotion chains. We create a pipeline, and how this pipeline works is we filter out tweets that have user, valid date, and at least one hashtag. We make one row. For each row, we look up other tweets with the same hashtag. We are canonicalizing pair order. We're deduplicating mirrored matches. We count how many coincidences each pair has per day, and keeping only the suspicious pairs, the output. But the problem that we occurred here is we did not find anything. And I tried changing the thresholds over here, and I tried changing it, and still I didn't get any outputs. So yeah, probably our dataset doesn't have one. I tried writing for more than 10 minutes. Even still, the dataset set shows no temporal mimicry. So probably the dataset doesn't have it. Moving on to section B, sandbox, which is over here. I created two sandboxes, which is one is the normal one and one is for graph data science, which we'll use it for the part B. So for part 1, initial graph data model, we're building our graph. So we do the links relationship, we're doing for the analysis, we create all this transaction client and all that. We're creating constraints and indexes. We were given CSVs, the client store purchase transfer. These are cipher codes, unlike the one that you saw before, which you'll use over here on the Neo4j sandbox when you open it with browser. Yeah, so here you can see all the node labels and relationship types that I've created. This is the code that we use to build the graph. You can see all the relationship types, the constraint and indexes, the provenance nodes that I've used, the loading clients and stores. What I did was I put the CSV files onto a GitHub, which is a public, which I made it as a public repository, and I loaded that CSV files from there. Part 2, initial queries. Problem 1. For us to find who spent the most on purchase transaction between these time period. So this is the question. We convert the AEST boundaries because the question had the AEST, but we put our file as UTC. So we convert the AEST boundary times to UTC first, and then this is the main subquery to find each client's total spend window. And for that same client, we find the top store, and we are picking the first element of the sorted list, which is the top store, and we're returning all clients tied for the same maximum total. So when you run this code onto the Neo4j sandbox, not the MongoDB shell, over here on this box, and when you click run, the output for that question is over here. The most spent on purchases on this fixed window is Logan Adam. You can see all his taxation count, the first taxation, the top story spent on, everything. Moving on to second question, which is largest negative cash flow. This is the code for it. So first, we are computing their outgoing and incoming paths with this subquery, and this transfers sent by clients and transfers received by the client, the incoming transfers. We combine components into per client totals, which is this code over here, and we compute the balance. We keep only the negative cash flows, and we take the top 5 of it. So this returns this one. You can see the top 5 negative cash flow clients. You can see their balance, which has in the negative form, the maximum outgoing, total outgoing, and total incoming. Moving on to the third question. The seller UTS receives pass-through funds from scam activity pass on. This is the code for it. And we're finding clients who receive money from others. Over here, get the seller stored node. And for each client, collect their purchases. For those purchases, we're collecting distinct qualifying transfers. They're computing attributed expert. We're breaking down by sender to get per sender totals, which is this code over here. Computing percentages, which is equal to total purchase divided by attributed expert, which is this, which returns over here. The pass on clients to seller words. You can see that the name Jackson Labber, the percentage, their total purchase, and the top spender. Moving on to problem 4. We write the cipher statement to create new relationship that connect ordered transaction as follows. Here, what we do is we're adding a sequence number for each client's transaction because our goal is to find ordering layer to the graph so that the transaction for each client are linked in a sequence. And we're creating next relationship so that we see their flow of their next transfer. We're connecting each client to their first and last transaction, and we're visualizing the client's transaction chain, which is like this. You can see that a client called Logan Adams, he first started out with this, and it went to next, and then you can see his last transaction, which is over here. Now, moving on to part 3, graph data science. For this, I created a new sandbox, which is over here. Blank sandbox, graph data science, this one. For that, problem 1, heterogeneous projection. The code for it is here, where we are required to build a heterogeneous graph with clients plus their shared identifiers, email, phone, and TFN. So first, we create the GDA sandbox and connect it to it. We're loading, since we're creating a new sandbox, we have to load the CSV files again. We're creating unique constraints. We're loading clients into databases. We're building identifier layer, which is required from the question. We're projecting the heterogeneous graph, the algorithms WCC and Louvain, which is over here. And we're computing group sizes and assigning persistent IDs, which counts how many clients per group. We're comparing algorithms and identifying the largest group. And we're visualizing this in the browser. This one compares how Louvain subdivides WCC group. You can see WCC ID, top Louvain ID, and the comparison. And this image shows you the graph visualization of the largest group which you're required to find. This shows all the clients and their shared identifiers on this. Moving on to problem 2, we're creating a cipher query that isolates cross-boundary transaction to tracking how funds flow into and out of these groups. Again, we need transfers, so we're using the CSV parameter transaction and this X for URI. We're identifying the cross-boundary transfers, building boundary graph and run clustering over here, and the centrality on the largest subset, which focuses on the biggest boundary group detected above. So we're running page rank algorithm and betweenness, which is page rank is weighted and betweenness is unweighted, to find the most influential suspects. So visualizing this, it shows the client and transfer inside the largest suspicious boundary. This is a cross-boundary recipients for the top 10 incoming fraud graph, and this is the centrality table which shows the page rank and the betweenness. This shows the client and the transfers within the largest boundary subset. Moving on to part 3, problem 3, which is link prediction. So this is the code for it, and since we need the transfer CSV file, we're loading the CSV file into the existing transfer, creating xfer_2 to edges with timestamps. These are the code for it. For projecting temporal graph into GDS, this is the code for it, and node similarity, which is required, and top 5 predicted links with time window. And persist predicted links, we use the parameter window days, 365 days, and this is the code for it, and we're saving that predicted link. So for this timeline visualization, we do 3 snapshots, which shows the predicted link at a different time windows, 75 days, 53 days, or last 3 days. You see temporal projection graph. We created a graph named temporal graph, which has the node count and relationship count. top 5 predicted client-to-client links, or 2 snapshots, which is so graph displaying maximum timestamp over here, 7 days to 5 days, and 3 days to max timestamp over here. And that's it for my COMP8210 assignment 1. We've covered every part 1, part 2, part 3 of the questions from both sections A and B, and we've shown the outputs, and we've shown the graph databases. We created sandbox and everything. The only problem here that why we didn't use the Bloom for the visualization is we can't run Bloom. I tried running it locally. I tried running it on the website. I clicked this open with Bloom. It said a license issue. I don't know how to fix that. So yeah, that's why I created the visualization on browser. I tried running it locally too. It still resulted in the server errors or license verification. So yeah, that is it for me. And yeah, thank you guys. Have a good day.